Hello everyone. Today we are here to present the ISC of the mechatronics or a micro-optical transducer for sensing application. Myself Pratiraj Kambe and my friend Akshay Sonavne will present this ISC. We have done this presentation under the guidance of RT Patil sir at RIT. These are the general layouts we are conducting in this ISC. First of all, introduction, optical simulation, fabrication and assembly, then design of a micro-optical transducer, conclusion and references. So let's start with our introduction. The optical signal transmission can be offer several advantages, particularly in miniature sensing application, namely a high degree of integration of signal sources, high-speed parallel communication to the electromagnetic interferences, that is EMI, by means of optical transmission channels, and eventually the possibility to apply the signal coding adopting wavelength division multiplexing, that is WDM. Tragedy is though the reducing the number of the transmission cable from the sensor array to mains of receiver. In the frame of this working, the primary needs was actually to design a miniature sensing module hosting MEMS sensor and a general purpose of electronics transducer to produce on a large scale and integrated on the flexible to work on the basic units of the sensing array. The main requirement of the module were to the relatively small in order to allow the satisfactory degree of a revolution in the skin flexibility, flatness and small thickness, and finally to able to acquire the sensory signal and optically transmit them by means of optical fibers. The last requirement followed by the aim to exploit a specific system for elaboration of the sensing data, which is based on a VLSI electronics implementation of a cellular nuclear networks. The signal input of this system consists actually in a CMOS detector, which is the first stage of a hardware design of for image elaboration. So now the further slide will explain by my friend Akshay.
Hello everyone, I will present optical simulation. In an optical simulation were carried out using the software Gemaxi and by means of ray tracking techniques. The primary scope of the optical simulation was to calculate theoretical performance of the transducer to be compared with a final experimental characterization reported in section 5. Hence, the aim was understood how much the performance of a real prototype could divide from those of a simulated structure, and this have estimation of the quality of the material using fabrication and assembly. Then the next part is fabrication and assembly. In the fabrication and assembly, the most crucial aspect of the entire module fabrication consisted in the need to assemble several different devices and structures on a small piece of flexible substrate using different technologies and processes, which can also affect each other. The optical system was the last to be assembled on the flexible substrate following standards surface mount integration of electronics first step and assembly of the three force sensors and their packaging in silicon envelopes second and third step. Then the whole assembly required time consuming processes since no automatic assembling machines were used currently not available among the laboratory facilities. In particular for mounting the LED and the optical coupler. Nonetheless, the entire process of fabrication and assembly of the optical system was conceived in order to be feasible with automatic machines for mass production.
So now I will explain the design of the micro-optical transducer. Figure number 1. The figure is a third quarter view of the first conceptual model for an unfolded flexible module de- to only one force sensor. The figure contains optical fibers, optical coupler with the 45 sloped mirror above the three LEDs, electronics, MEMS force sensor, and flexible. Figure number 2 shows the third quarter top and side view of a CAD model of the micro optical transducer fabricated for 9 optical channels. Figure number A shows the 0.5 mm diameter plastic optical fiber. Figure number B shows the critical layout metallic optical coupler. D shows LED with the bound wire, the second seg in, the numbering of LED channel used in the text reported.
Figure shows design of micro-optical transducer. Nine commercial LED ties. They emit radiation with wavelength of about 650 nm visible red, and they have a size of 275 to 75 mm. A metallic optical coupler with a size of 6.54 1 mm3, which has the role of reflecting the light emitted by LED into the fibers by means of the 45 included reflective slides created inside the metallic coupler, preventing drastically reducing the crosstalk about the optical channels, packaging fibers and limiting their insertion, preventing rupture of LED bond wires, protecting LEDs and bonds wires, allowing rough handling of the whole module, conferring robustness and stiffness to this delicate part of the transducer. The next part will be explained Prithviraj.
So here is the conclusion. A micro-optical transducer or a terminal consisting of LEDs and a metallic optical coupler and a plastic optical fiber was developed by means of microfabrication and a microassembly technology and integrated in the hybrid op- op- optoelectronics module on the flexible substrate. The assembly produced were the successfully tested and the micro-optical system fulfills the initial requirement, performing well in the sensing application. These are the references where we take the information of the micro-optical sensor. Thank you for watching our video, and I hope you have learned something from this video. Thank you.